Okay, so today's topic is about SPI and I2C. So, okay, those are the most common digital sensor interfaces, or actually any device interface when you're talking about connecting to the microcontroller environment. SPI is really widely used with high-speed requirement devices, and I2C is then, well, rest of them, I would say. The both has some history. Let me go to the, where's my mouse now here? Open that one into different, where's the slideshow? There. Oh well, I'll just show it like that. So, about serial communication overall. The serial communication can be actually divided into two categories. One is asynchronous. Asynchronous, where you basically have only the data line, which means that basically the synchronization is done locally, which means that both the sending and receiving device should know exactly what is the clock rate on the data transfer. One good example of asynchronous clock signal is what the old-fashioned serial port or UART, the normal way of using UART. UART is universal asynchronous receive and transmit, but usually UART circuit also can be used in synchronous mode. But anyways, if you don't have a clock signal online, then it's asynchronous signal. And then the synchronous has data and clock signals on the devices. So basically, there is a common clock rate for the receive and transmitting, which makes this one basically easier to implement on hardware. Okay, so basically, if you look at a serial line data overall, the asynchronous lines usually start with idle, and then with the start bit, and then you have the data bits, followed by the stop bit. That's a usual way of transmitting. Basically, the start bit tells, this edge tells when the local synchronization should be starting, and then there's also the stop bit, just to have a gap between these consequent transfers. But this is in general level. Where is the beef? Okay, universal asynchronous receive transmit circuit is a bidirectional asynchronous the module, and basically, well, there is some theory about it. I don't think that this is basically anything big here. Refer to datasheet for more information. This is history where the serial asynchronous lines actually came from. Before PCs, before you were born, before, actually first serial lines appeared sometime in 70s. So I was in elementary school, and the first computers were big and did less than what my wristwatch does. So, but there was already need for communication, so basically a serial line communication was selected for two good reasons. Simplicity of wiring, since the most say painstaking operation on communication is always connecting the wires. That's why in most cases you need only pair of wires on data transfer, just like the asynchronous data subscription lines, ADSL, if you have that kind of old technology at home. Okay, the last era of the copper wire transfer. Now the transfer is done with these kind of things, so that's the way it goes now. So if your dad started waiting for that optical fiber, you can show that one to him. It never came, so optical fiber never came to home. Okay, but anyways, so usually this normal, the old-fashioned serial line has dedicated transmit data and dedicated receive data, and then of course the signal and ground. Just like in this board, actually, this programmer has the USB UART bridge, meaning that when you plug it into the computer, principally it opens the ISO 6 level driver is actually the old-fashioned serial port driver. It shows like as a COM port. And for this one, you are actually, there's a connection from points 12.6 and 12.7 are the receive and transmit data, respectively. Okay, so signals are still there, and this can be used still between the devices. And it's easy, standardized way of transfer. Good thing about this is actually you can transfer data quite far away with some buffering. So basically, I have myself done a 4.5 kilometer data transmission with just with the ordinary telephone lines. That was before we had reliable modems. Okay, and it was a slow transmission. In addition to these three, the original RS-232 or EAI 232, they were also handshaking signals, which also have a couple of funny lines here that tell us about the history. So this standard was done on the era of modems, which made that funny sound. Okay, RI, ring indicator. So basically a separate line for answering the phone by the modem. Another signal, carrier detect. That basically, if a modem is making a call, it must wait for the carrier signal, which is just a but you cannot hear it anymore. Everything is digital. Okay, and then there are some voltage levels, but that's history, and I keep it there just because you need to know a little bit of the history too. Okay, usually all the devices like microcontroller or this chip here, this programmer part, they are defined as data terminal equipment, which also comes from, history. I started my study with watching green terminal, CRT terminal with green letters. And that was a fancy terminal. This was actually this enhanced with graphics, meaning it has a special character set of line to do some line graphics. Wow. Yeah, I feel old. Yeah, for a good reason. But anyway, so basically if you have two data terminal equipment, then basically one is transmitting, another one is receiving. Then there's a ground. There are some exceptions if you have a communication device. It could be actually that the other device is defined as data circuit ending equipment, meaning basically the computer end on the old-fashioned way. Then you would connect transmit to transmit, because for that DCE point of view, transmit means input. Okay, just for you, that you don't get confused if you ever end up designing that kind of things and you have a communication circuit. Okay. Yeah, good. Modern PCs haven't had the physical RS-232 ports for 10 years. Maybe desktop computers you can still buy one used. But the laptops have had the USB and USB comes with a, since USB 2.0 there has been the virtual COM port, VCP. Okay, and that's what you have been using on the computer end to communicate with that one. Okay, yeah, there's also about some things about the this prototyping kit. Okay, so that was basically the something between our black box and PC. How that communication is done. On this one, it is loaded with history, but anyways, it works. It still works. Everything is built on the top of the history. That gives us the foundation. Okay, serial bus. Fundamentally, a serial bus concept means that we can have multiple sensors sharing a bus. That makes it a bus. So basically, what you had previously, this one is not yet a bus, it's just a data connection. But what makes it a bus is that you have multiple sensors, which means that you need to have some sort of addressing. And the addressing actually depends highly on what kind of bus you have. But anyways, yeah, one serial bus is the CAN bus, which is commonly used in most of the cars. Standardized, industrial standard bus. Okay, one wire. I start with the one wire because actually it's quite nice concept. Dallas Semiconductor, and again, ancient technology, still in use because of its simplicity. So you have one wire master, meaning your microcontroller. You have both transmit and receive lines are the same. There are different ways of doing that actually. So basically receive, it just means that you are listening the pin. Transmit means that you are actually accessing the pin, changing the mode, for example, drive mode. And then you actually, these devices require only this ground wire reference wire, and signal wire. These are very low power devices typically, and it can actually generate the power from the data line. They usually draw, say, in standby mode, less than 1 milliamp of current. So very low power devices. Okay, actually they usually also need a capacitor to act as a charge bank, but anyways, the bus itself is only one wire with branches. Okay, simple. And yeah. Yes, the downside is a low data rate, 16 kilobits per second. It's nothing compared to any other. But still, this is used in, say, slow applications like temperature measurements. There's a Dallas 1820 type one wire temperature sensors. They cost something like nothing, and wiring is easy, and there's plenty of code examples available. So that's probably the easiest and cheapest way of measuring temperature. Okay, and that's about the parasitic power. So the parasitic power actually would work, and they on inside of that device, they usually are the rectifier that basically, and small capacitor which may be actually also outside of the device. So it basically charges that device whenever there is a data line is up, and that's actually the idle is the high signal. Okay. Okay. This is old information. I should have actually taken it out. Unfortunately, are they testing some? Okay, good. Testing, good. No worries. Yeah. So, unfortunately, this device does not have a component for one wire. But there are plenty of examples if you ever need to do something with the one wire. And it's very simple protocol, very simple slow protocol that you can actually do a software the driver yourself. It's just about setting this one signal pin, either 0 or 1, and listening with the and following the protocol. Simple to do. It takes some time though. I would say it would be 1 full working day of doing it from the scratch, or 15 minutes by borrowing somebody else's code. Okay. So, but anyways, these one-wire device applications, okay, I button, that used to be a big thing, although it's not anymore. I think it's obsolete technology already. It was a big thing 10 years ago. Then some real-time clocks, because, well, real-time clocks they usually have either their own power source or they have a battery inside. But anyways, they are very low power consumption, and the real-time clock does not need to be accessed so often. Only usually when you are booting a computer, then one wire real-time clock will be just fine. Temperature sensors, of course, there are plenty of those. An example, DS18, S20 by, that's maximum, well, basically, that's maximum Dallas semiconductors. Okay. Then another bus, I2C. So actually, that number 2 comes from the, it's actually an exponent. So it's IIC, Integrated Circuits Bus, developed by Philips, a Dutch company. That's probably the only Dutch product that has some use. Sorry, that was a bad joke. The thing is that in the 70s, Philips was equal to bad quality, low price in consumer products. That was in Europe. Since then, people have been just joking, whatever comes from Philips doesn't do anything. But anyways, Philips made this I2C bus. It still holds the trademark. So if you are working for a company which is not subsidiary of Philips, and you have a device, don't call it I2C. Since you can always use 2-wire interface name for the interface. Then it's not the copyright violation. Okay, so I2C is a synchronous bus. 1 wire is asynchronous. As you saw, it was only 1 wire, so no clocks there. The I2C is a synchronous bus, which means it has 2 wires. One is for data in and out, and another one is clock. The serial clock is driven by the master, and the data is actually a common line. And both lines actually have a pull-up resistor, which means that basically these lines are driven by open collector or open drain. The drive, meaning that when you want to set 0 into line, you pull it down. But normally it's either idle or state 1. Okay. A bus actually contains 1 master and multiple slaves, up to 127 slaves, which is a lot of devices in 1 circuit board. So the design is so that it should not be used between, separate devices unless they are on the same circuit board. Okay. And but there are also ways to extend this bus to separate circuit board, as long as it's a short distance. Anyways, so each device has 7-bit address, which is not much, which means that there's also another addressing mode. But the basic addressing mode is 7-bit addressing mode. There's also extended addressing mode, which uses 11 bits. But anyway, so again, master is the master, so basically it's responsible of everything that happens on the bus. It basically makes the address followed by a command, and then these devices should reply accordingly. All right. On this kind of bus, it's really important that there's some specific protocol for starting a transmission and ending a transmission that everybody knows. Starting of transmission means that we have, okay, that's the clock line, this is the data line, sorry about the offset. So we have a clock line high, and the data line actually goes low. So that at the same time as clock is high, if you have a data line going low, all the devices know there's a start of transmission. Then basically it's followed by the address byte, 7-bit address, and ending with if this is read or write. Okay, so basically after that 7-bit address, if there is a device that fits that, recognizes that address, it sets the acknowledgement. Okay, and either listens the data or writes the data according to this serial clock. And after every byte, basically, there is an acknowledgement on the receiving side. So if the device is getting the data, then it actually acknowledges, okay, transmission done. This way you can actually continue writing to the same device a burst, data burst. Okay. And that one is actually ended. The data transmission ends when the clock signal is high and you turn the data from low to high. End of transmission. Okay. That's a basic communication of 1 byte. If there's receive and transmit and receive at the same burst, basically what you would do at the middle is restart the transmission. So basically there's a start, address, followed by the read or write, or actually it's write, always write with the command byte acknowledgement. Then you have repeat the start condition, meaning that you change the state of the data line low and high during the clock cycle, and then the same address with the read bit, and then you can continue the data transmission. The end of transmission actually can be also marked with the with letting the state to be not acknowledged. So not acknowledged may mean that okay, transmission was okay. This is just the end of it. Okay. So yeah, that kind of, it's kind of smart way of sending data. Okay. Some example devices, so temperature sensors. We actually have that TC74 here. I think these are the 5-pin TO220. Someone younger could read it. They should be these actually. Big can for historic reasons, or actually this temperature sensor can be used to monitor power on some, say, these what are these? The cooling grids. That's one of the places where these are used. Usually not the room temperature. That's not a good case for that. Then there are, for example, I think this is originally Motorola. Now I think it's Infineon. 3-axis acceleration sensor has I2C, and they're basically, it's that small chip here. It's one of those QFN cans, very tiny, about 3 times 3 millimeters. That's a little bit tricky of soldering, especially with these. Okay. TCS3414, a color sensor. Okay, which basically has this color sensor has these photodiodes with some filters on the top of them. Then real-time clocks and so on. The I2C devices, there are plenty. And actually, I2C bus is also used sometimes between processors. That's a simple way. In addition, at least 15 years ago, there were plenty of computers which has the boot code on EEPROM, which was on I2C bus. Because you need to boot the computer only, 2 times a day at that time. So the BIOS code actually was on EEPROM, which was on I2C. I have no idea how the chipsets nowadays work for the computers. Okay. There's one temperature sensor like that. Yeah. Okay. Actually, this is pretty useful device if you want to have a self-working thermostat for some application. So basically, you can use it as a temperature sensor, but there's also internal comparator that you can write the value, and there's basically if temperature goes lower, higher than that, there's a line to drive a, for example, transistor to turn on either ventilation or heat or whatever, or just turn on the light. Okay, then about the extension, SM bus, system management bus. It says that it's used in many computer systems to manage power. Yes, it is. Because it's simple, rugged, and it actually works. And okay, it's based on I2C bus, but okay, it's extended somehow, so it's basically Intel trademark on SM bus. All right. PSoC and I2C. This is actually for the PSoC 1. The similar things actually are also for this PSoC 5 what we are using. So they are so I'll just leave it like that. Okay. That was the I2C. The second of today's exercise. So today's exercise actually have both I2C sensor and a little bit more complex SPI. Well, the SPI it's simple, very simple, but you will be doing more connections. SPI is also a synchronous full duplex bus. Okay, the I2C is actually half duplex, meaning it uses only one data line. So it's a bidirectional data line. In SPI, you have 2 data lines. One, this is called MOSI, master out, slave in, that way. And then you have another line, MISO, not the soup, but the master in, slave out. And yeah, these are not politically correct ways of naming any pins. It goes directly to the dark ages of human history. But well, it's history. Hopefully it stays history. Then it also have the serial clock, which is again driven by the master. These three lines, actually if there are multiple sensors, they share same serial clock, MOSI and MISO. Addressing is made with the chip select. Old-fashioned good chip select. So there's nothing wrong with the chip select signal, especially on SPI. Okay. That's quite interesting. SPI comes with all sorts of data rates. The first one what we had was this one wire. It has that 160 kilobits per second data rate, period. It does not change, it's there. I2C, there are slow devices and fast devices, and I think there's also that ultra fast devices now. So you need to check the data sheet and don't put different speed devices on the same physical bus. There is a limit on I2C because it's you cannot use these matched lines. So you cannot use impedance balanced lines, meaning that it's usually up to few megahertz maximum. No, 400 kilobits per second, I think that's the maximum in practice. SPI, there's no speed limit, which is good. But only in electronics. I'm really in favor of highway speed limits. The 10 megabits per second is easy when you have short distances. Since you can actually have strong drives on both ends, you can actually, if you want to have a balanced lines, you can use balanced lines here. Nobody is telling you not to do so. So this is the favorite choice of memory buses. If you have serial interface on memory, it will be most probably SPI. Example of that would be those SD cards. SD card has a SPI bus to access the memory. Okay, yeah, with the multiple devices, I already said that you have one single the bus, but separate chip select lines. All right. Okay. The SPI is also a bit, say, a little bit too vague a standard, since basically it also then gives too much of freedom of choosing what kind, when the data is ready there on the line. So there are different modes. You need to check the mode of the device. It's one of those 3 or 4 modes before you can actually access it correctly. Since mode 0, read the data on leading edge, clock edge, clock not inverted, or data is read on the leading clock edge, but clock is inverted. And then, of course, trailing clock, not inverted, trailing clock, inverted. Depends totally on the device. But you have access to these modes also on the software side, so as long as your software knows which mode the device is, you can change the mode on flight. And this is kind of bus that you can have different speed devices on the same bus also, because the device doesn't do anything if it's not accessed by chip select. Okay. And there's some more information about it. Yeah. SPI sample 1 byte sent to microcontroller, sent from the microcontroller. Right enable goes down, that's the clock, and then serial in of the, let's see, yeah, that's MOSI signal. Yeah. And basically it has sent, okay, it has sent either hexadecimal 0, that's 6, right? Yeah, or 6, 0. Another thing which is not defined, which order the bits are going. You always need to check it from the device. Most of them actually go most significant bit first, I think, but check it from the data sheet. Same thing for the from a microcontroller, 1 byte from microcontroller and 1 byte to microcontroller. This is a kind of bad example, since you can't transmit read and write signals at the same time. You have to do 2 different signals there. Okay. So the difference between I2C and the SPI is that I2C is lower, long range, well, long range, define long, no, it's not really a long. SPI is for speed. SPI interface devices, okay, TC74 also comes with the SPI. You will be using the I2C there. Then, for example, this kind of accelerometer, some digital parameters, flash memory chips. So basically, if you put a flash memory chip on SD card, you can access like that. Yeah, SD or MMC cards. Yep. Some radio modules. So basically networking devices where you need some speed for data transmission. And then some obsolete information about this one, since this is for SPI, the PSoC1. Okay. SPI can be quite easily extended. The distance can be extended, for example, using this standard EAI 485 or EIR 4222 type of buffers. They are just line buffers that are designed for pair wires, meaning this the matched pairs. Match pair lines, impedance match lines, and distances 100 meters or more. Easy. You just need to make sure that you don't get much of reflections or too much of attenuation on the line. meaning good impedance matching. Okay, yeah, some summary. SPI summary. Synchronous full duplex bus for short distance communication, high speed. And actually, nice thing also about the SPI, I used to have an exercise to make a software SPI. Since it's synchronous and not that critical about timing, then of course you can run one digital output as a clock with software and then do the write another as a MOSI and then have one signal input and read it as a MISO, have one output as a chip select. So you can do full software SPI that's quite straightforward actually. That's all. For the theory part. Okay, let's take a quick look at the exercise. Okay, so yesterday you put the analog sensor to the system and you had it sampling and everything. I think today you can actually start from yesterday's exercise. And if I'm correct, yes, I think everyone has returned yesterday's exercise. Thank you. I have, let's see, do I have enough of names in 10, 11? Yes, I have the same amount of returns. Good. So you have something to start with. So you can start with the yesterday's exercise, make it as a template, and then start a new project. Check that it still works. If not, then you may actually borrow somebody else's design. Make sure that it works first. And then yesterday you have this analog sensor. Today you will add I2C sensor. That's also temperature sensor. That's the one. TC74, I think. You have better eyes than I do. Right. Read if it says TC74, please. On the can. Somewhere in the can it should say TC74. Okay. That connects into the PSoC on I2C module. After you have added that one and tested, then you put SPI sensor, which is not just sensor. There is MCP something. MCP, was it 1206? No, something else. This is a 8-pin package which has SPI interface A to D converter. 12-bit A to D converter. Haha. Then, in addition to 12-bit A to D converter, there is NCP1541, which is, let's see, was it 1 point? No, it's actually a voltage reference of 4.096, meaning 2 to the power of 12 millivolts. So basically, if you have this voltage reference and this A to D converter, you get 1 millivolt for each bit. In addition to that, you would need, not that one, you probably would need some, not resistors for that one, capacitors, yes, bypass capacitors. Okay, so that's for the SPI, and of course wires. By the way, with the I2C, you need pull-up resistors. So pull-up resistors for the I2C. Okay, next. So those are the devices. So select these as here on your device. Yeah, I'll connect MCP3201 is the SPI bus, A to D converter, and read the data sheet. It's right behind of that link. And actually, you, as a signal, you can then connect this analog sensor also to that one. So you take the analog sensor, you still have a connection to the analog A to D converter of the PSoC, but also to this external A to D converter. Then you can basically compare which one is better. That's the voltage reference. Read some notes, how to use SPI. Okay, I hope this note actually is the correct one. Make sure that it's the note for PSoC 5. And then port 05 is serial clock, port 04 is MISO, port 03 is chip select or slave select. You don't need MOSI, master out slave in, since that A to D converter does not take any commands. It's just the input device for the processor. Okay. Then another connection is the I2C temperature sensors. It's up to you which way to go, which temp sensor you will check first. Do not do everything at once. Make either the SPI bus first or the I2C bus first. But anyway, so basically you connect that one. Port 07 is serial clock for that one, and port 06 is serial data. And okay, you also need those pull-up resistors for the I2C bus. Unless, I'm not sure how large these pull-up resistors inside of PSoC are. It might actually work even with those. But if the pull-up resistors are too big, then you may end up in trouble that the line does not release fast enough. Okay, and again, you just extend yesterday's exercise and put also the information about these two other sensors as the output. Yeah, good. That's the exercise. And since you did so good job yesterday, I'm also expecting you to do a good job today. So the fourth exercise deadline today, before the day ends. Then couple of words. You have been really a good group, so I would recommend you, if you want to, take the longer version of this course. And do also those the other optional exercises. So let's go to home here. Oh, come on. Why it doesn't do anything? Oh, do I have network? Yes, I have network. Ah, there we go. So, exercise 5 here, that's actually the one wire. It takes about full day. There's instructions how to do it, but mostly you just add to the today's design. You will add one wire temperature sensor and start reading it. Just one remark on that one. One wire is very slow, and that device is also very slow. It cannot be read more than once a second. So actually it's something like 900 milliseconds that it takes in between the samples. It's very slow device. Okay, so if you do that fifth exercise, you will already receive one more credit. So otherwise this is 2 credits because it's 4 days course, 2 Metropolia credits. You do this one. It's, first of all, it's you know, I'm not here. You work more, and then basically it's gives you 3rd Metropolia credit. Then, if you wish, you can also make a project. I will show you a couple of those project topics. It's more or less a you can also have your own idea of the project, as long as it's what? No, I think I have problems with the network now. There, okay, yeah. Network project. How many of you have been working with the Raspberry Pi? You know what is missing from Raspberry Pi? It's the it's the A to D converter. Okay, one way of doing the A to D converter would be to use the PSoC board as a A to D converter. If you do this one, please make it a multiple line. So basically you can have up to 8 analog lines in, and was it maximum 2 or at least 1 analog out line. So make a nice A to D converter kit based on this processor for Raspberry Pi. So 8 analog channels in, 1 analog channel out, and test it on Raspberry. You would get famous on the Raspberry Pi community. You publish that one and everyone go, ooh, wow, we have been waiting for it. I'm sure that you can do it. Another one is a greenhouse option. Anyone having your own small greenhouse? I'm not asking what you are growing there, but greenhouse. I have actually myself, I'm a hobby gardenist, so I have some property on my backyard, and I have 3 different greenhouses there. So because Finland the summer is nice but short. If you want to grow, for example, peppers, you need to have a greenhouse. I grow leeks there, and something else. Yeah. Some spices like let's see, what is that? Basil. It doesn't really grow outside, so I have a greenhouse for that. So I have three greenhouses, and I have dreamed that at some time when I will have any time for my own, I will build a greenhouse automation, meaning the ventilation for heat, and maybe some sort of thermostat to turn on heating for these cold nights in September, and then of course the irrigation system. What I would like to see is just the brain of that one, meaning the sensors and some LED light showing that, okay, now the ventilation should be going on, and or now the heating should go on or off. Now there is actually need for watering. Just the indicator LEDs, since those can be easily switched into the transistors, or those nice devices that you can plug AC devices just and run it with a single line. Or if you have a better topic than these two, you can also, okay, I have this kind of idea, would it work as a project? So if you have some extra time available, why not to use it for learning more PSoC and doing something useful? So option 1, you would get famous, definitely. I haven't seen any really working approaches to data acquisition add-ons for Raspberry Pi. This would actually give one simple solution. Since all the hardware is already there, you just need lines, input and output. The greenhouse automation, as I said, it will be for me. If you think that I'm a nice guy, then you can. Of course, you would do it for me. Okay. And then when you have done the project, you would receive full 5 credits from this course. Doesn't sound good. Haha. Okay. Which means as well, today is the deadline for this 4th exercise. Then the 5th exercise, one wire exercise, there is some more time for that one. So that one wire. So I will mark something here. Basically, there's no hurry since I will be in Frankfurt on April. So I would say around mid-April would be deadline for this exercise. And you will be returning exactly the same way as you have returned this far. And then deadline for the project would be, I think I have the deadline already marked. No, I haven't. Okay. Usually I have the deadline at the end of the Finnish semester, which is around mid-May. It gives you some time to actually work on the project. Okay. So that kind of options. Let's take a quick look at yeah, that's fine. Okay, I will create a new project now, just for fun. Okay, I don't know. I just start with that template. You would start from yesterday's. Make yesterday as a template and start from there. But I would just click buttons here. Doesn't do the matter. I'll just have a quick look at those modules, or not modules. These are components. Where do we have? There's the SPI component under that one, and there's I2C component under that one. So SPI component, basically you would need that SPI master. That's the standard, the SPI controller with master in, slave out. You would need that pin, of course. Clock. Read the data sheet and see how fast your clock can be. that device, you can use it up to, was it 1 mega samples per second. So you can have 60 megahertz clock there. But check the datasheet. Don't believe me. I make mistakes. I don't recognize those myself, though. But somebody has told me that I have made mistake once. Okay. Then serial clock and chip select or slave select. If you had multiple devices, then you would actually take this one and have a address multiplexer here, chip select multiplexer, to access different devices. That's quite simple actually to do. Single chip select, but then you have a logic circuits here to do the multiplexing so that you will access exactly some specific device. But now you have only one SPI there, no problem. Okay, just read the down manual and start using it. Okay, then I2C. That first one is slave, meaning that the easiest way of using this circuit as a device is to have I2C slave on it, for example, for that A to D converter thing, meaning that you have software access to the data that some other device is going to read. Okay, so you can use this as a I2C device where a external microcontroller can read or write access certain memory location. Works, and probably the easiest way to connect to Raspberry, since there you have the I2C, you can even write, say, higher level language code with the Python to access the I2C bus. Okay, but okay, they are different. You need a master, fixed function, or UDB. This is universal device, meaning it's basically, I haven't told you much about that one, but basically it has something to do with this resource meter here. That one shows how many resources we already have on use. Oh, it doesn't really show, but this is. Oh, okay, it doesn't show because I haven't done the generate application yet. All of those devices, when you add modules or these components to the design, they of course reduce the amount of available resources. The same way as in FPGA design, you need to figure out, okay, does it say no? No, it doesn't. I cannot read that at all. No, I can't read it. There's a resource meter, and they are universal devices, meaning those are digital blocks, general digital blocks that can be then reallocated in different blocks of the physical device. Then there's also the fixed function, meaning there is a I2C master controller, dedicated controller in that chip. You can use that one too, either as a master or slave. So in that sense, it doesn't really matter which one you use, fixed function or. Okay, it seems that the biggest difference is that you do not have in this one, it seems that you don't have the clock. Oh yes, you have the clock. It's basically, if you use the fixed function, then you click the data rate here. If you use the UDB, you can actually route a separate clock signal there. But I think this is the master fix function is easier to use. And you can actually, this is fun. There's a selection to change this one to UDB. So practically they are still the same design. Okay, so that's the I2C. Those two components, and then you, of course, you need to select lines, read the data sheets, and do the magic, make it work. Make me proud. Okay, thank you first for your attention. Now it's your time to start doing the exercises. I will be here until 4-ish or something like that. So I'll be here so checking that everything goes right, and if you have any questions you can answer. I can answer to those. So okay, your turn to start working. Thank you.